Lesson 2.2, exponential functions. The last lesson, we did a lot of work with exponents, and we're going to be using this today. Well, first thing I have here is, what is an exponential function? It's of the form, say, a to the x, where a, we call this the base. This is positive, not equal to 1. So I have two charts here. The first one, you see I have bases bigger than 1, and this one I have two bases between 0 and 1, and we will evaluate these exponential functions. Okay. Well, 2 to the minus 2, if we recall from our lesson last time, we can write this as 1 over 2 squared. And so this is 1 over 4. And then 2 to the minus 1 is 1 over 2. This is a half. Now 2 to the 0, this is 1. And then we have 2 to the 1, which is 2. 2 squared is 4. And 2 cubed is 8. So evaluating here, we have 1/4, 1/2. We have 1, 2, 4, and 8. And we should see these on the graph. Well, this orange graph is 2 to the x. We can see it just based on what we've evaluated, because here, this point is the point 1, 2. We have the point 2, 4. We have the point 3, 8, 0, 1, and then we also calculated these two. So this is the graph of 2 to the x. Well, now for 3 to the x, you see it's very similar. We get 1 over 3 squared, which is 1 over 9. We have just 1 over 3 here, 1 over 3 to the 1. We have 3 to the 0, which is 1. And then we have 3. We have 3 squared, which is 9. We have 3 cubed, which is 27. So this is the function value of 3 to the x at these different x values. And if we look over here, that's this blue graph. This is 3 to the x. Well, both 2 to the x and 3 to the x go to the point 0, 1, but here you see 1, 3, and we see at the very top, it looks like 2, 9, and then we have these other points here. Now, in fact, graphing 1/2 to the x and 1/3 to the x is quite similar. You might see you have these two graphs, and these, we are just reflecting them across this line. But let's understand why that's the case. So when we take 1/2 to the x, if we think about our lesson last time, properties of exponents, really it's 2 cubed, because it would be a 1 over 2 to the minus 3. So this is really in the numerator. So this is 8. And here we have 2 squared, which is 4. And here we have 2 to the 1, well, which is 2. Here, well, 1/2 to the 0, this is 1. But now we have 1/2, and we have 1/2 squared, which is 1/4. So you see these values, we see them in the chart above. It's just that on the graph of 1/2 to the x, really you are replacing x by minus x from the graph above. That's this reflection I was mentioning. So we have calculated it. And 1/3 to the x is very similar. This would be 3 cubed, which is 27, 3 squared, which is 9. This would be 3 to the 1, which is 3. We have 1, 1/3, and 1 over 9. I will highlight these so we see all the function values. It's here, 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 here. So the orange one is this 1/2 to the x, and the blue one is y equals 1/3 to the x. But it's also important to understand, because of properties of exponents, this graph you can also write as 3 to the minus x. And this graph you can also write as 2 to the minus x. So that is an important comment as we first think about these graphs. Well, let's remind ourselves some properties of exponential functions, and they are here. So all of these we discussed last time and used last time, and we will be using them again. But there's one more property that we've seen on the last page that is definitely worth mentioning, and that is a to the 0 is always 1. And so in particular, no matter the base, the point 0, 1 will be on the graph of the exponential function. X equals 0, y equals 1. Very nice. Maybe I will put it here, 0, 1, and 0, 1. And this picture shows you the basic shape where you have a base bigger than 1, just like we saw with 2 to the x and 3 to the x, and the basic shape when you have a base between 0 and 1, just like we saw with 1/3 to the x and 1/2 to the x. Now, no matter the base, okay, provided you have a positive base not equal to 1, the domain of these functions is all real numbers, minus infinity to infinity, but the range is not. You notice, just looking at the graph, the range is 0 to infinity. We only get positive numbers as outputs of these functions. And another important thing to notice, for a base bigger than 1, which is a basic shape like this, as x grows without bound, that means x is getting larger and larger and larger. Well, you see the function, so a to the x, also grows without bound. Moreover, if you have a base between 0 and 1, the basic shape is a picture like this. As x grows without bound here, you see what happens. The function is, well, it's getting smaller and smaller and also approaching 0. I will say a to the x decreases and approaches 0. Because of this behavior here, which we see visually in the graph, for base bigger than 1, the exponential function grows without bound as x grows without bound, while we typically refer to this one as exponential growth. And similarly, when you have a base between 0 and 1, well, the function decreases and approaches 0, and we will refer to this as exponential decay. When you have a base between 0 and 1 for an exponential function. So this is terminology that you could have seen before, but it's also important to understand, as is, well, once you get to calculus, say this behavior of functions as x grows without bound. Well, here's an example. F of x is 3 times 4 to the x plus 1. Let's evaluate. We've done this for 2 to the x, 3 to the x, 1/3 to the x, and 1/2 to the x. But here's another example. We are going to evaluate -3 at -1. We will evaluate at -1/2, and we will evaluate at +1/2. We have 3 times, well, 4 to the -3 plus 1 is -2. So this will be 3 over 4 squared, and 4 squared is 16. So this is our first evaluation. At -1, we have 3 times 4. -1 plus 1 is 0. So this is just 3 times 1, because 4 to the 0 is 1. So this is 3. F of -1/2, we have 3 times 4. Well, -1/2 plus 1 is +1/2. So 4 to the 1/2 is 2, square root of 4. So we have 3 times 2, which is 6. And we have one more to evaluate here. We want f of +1/2. This would be 3 times 4 to the 3/2. 1 plus 1/2 is 3/2. Well, we discussed this in the last lesson. One way to approach this is take the square root of 4 and then cube it. Let's do it this way. So this would be 3 times 2 cubed, which is 3 times 8. This is 24. So here are these 4 different function values. We had to use properties of exponents here. Now here's 2 wonderful questions. The first is, the square root of 9x, an exponential function, justify our answer? And then same question for -5 to the x. The first one, I will say the answer is yes, but we need to see why. And its properties of exponents. So note that this is 9x to the 1/2 power. Well, there's a few ways we can think about this. It's power to a power we multiply. So this is, maybe I'll do this in 2 steps, 9 to the 1/2 times x. But I can also write this as 9 to the 1/2 to the x. Right? Power to a power we multiply, power to a power we multiply. These are both equal to just 9 to the 1/2 times x. But writing it this way, 9 to the 1/2 is 3. So this is 3 to the x. So this is, so yes, we can see it. In fact, the base is 3. We just had to do some properties of exponents to realize we were looking at an exponential function. But the second one is no. The reason this is no, well, think about this. A short answer is -5 is not a positive number, but there's more we can say. The domain of this function is not here, -infinity to infinity, which we must have for exponential functions because, for instance, f of, say, 1/2, which would be the square root of -5, is undefined. So for example, 1/2 is not in the domain of the function. Yeah, not a chance. Is this an exponential function? And so I can just add this, which I just said, 1/2 is not in the domain of f. So in particular, the domain is not -infinity to infinity. Our next few examples, we're going to be solving exponential equations. And one thing that we can use here is the following. If you have a base, a needs to be positive, not equal to 1, then if you have the same base, that's what this is saying. So a to the x equals a to the y. This implies is equivalent to x equals y. Okay, so you have same base, we may equate exponents. That's what this is saying. We have the same base, equate exponents. This is what we want to do. Now, the first step in all of these is we want to get both the left and the right-hand side to have the same base. Once we do, we may equate exponents and solve. Well, this first example, you see, I see 36 is 6 squared, so this will be my same base. So here on this side, I have 6 to the x plus 2. I can take one small step here, maybe as part of my work, write this as 1/6 squared. Now I can do this, right? 6 to the x plus 2 is 6 to the -2. Now I have same base. I may equate exponents. X plus 2 equals -2. And now we just solve by subtracting 2 from both sides. We have x equals -4. So this is my answer for this one. Now let's move on. The next one, 4 raised to the x squared minus 9 is 1. Well, you might question, how am I going to get a same base or like base on both sides? We have to remember, though, that we can write 1 really with any base as just that base to the 0. So this is what I want to do. I see the base of 4 on the left-hand side, and I want to write 1 as 4 to the 0. You see how nice this is? Because now I can just equate exponents. We have x squared minus 9 is 0. And I can, for example, factor. And I get that x equals 3 and -3. Well, let's move on to this one. We're going to have to do multiple things here. On the left-hand side, I see power to a power, and so I will multiply. But before I start doing this, my same base or like base is going to be 3 because I see it here. Also, here's 3 to a power, and I can certainly make 9 as 3 to a power. So now we will start. Left-hand side, Power to a power, we multiply. So the left-hand side is 3 raised to the x times x plus 2. Well, my right-hand side, this one is 3 squared, and then I have 3 to the 33. We are going to use another property of exponents here, because here we have 3 squared times 3 to the 33. This is going to be 3 to the 2 plus 33. So let's take another step. We have 3 to the x squared plus 2x on the left. We have 3 to the 35 on the right. Now I'm going to equate my exponents. So I have x squared plus 2x equals 35. So let us subtract 35 from both sides. We have x squared plus 2x minus 35 equals 0. And then we have to think about how to factor here. I need two numbers that multiply to negative 35 and add to positive 2. How about negative 5 and 7? So let's do x, we'll check, minus 5 and x plus 7. Multiply minus 5 and 7, we have negative 35, and add them, we have positive 2. And so this works very nicely. Well, now I can just write down my answer. I get that x is 5 and negative 7. Here's the last one on this page. Well, I see a 2 to the on the left-hand side. And because I'm going to be using like bases here, I want to get a 2 to the on the right-hand side. And then, well, we also see an absolute value. So we're going to have to remember some things from our absolute values lesson. But my first step, because off the top of my head, I don't know the cube root of 16, nor do I know the cube root of 2, is I want to simplify this. So this would be one property that we practiced last time of exponents, is this would be the cube root of 16 over 2. So 16 over 2. But this is just the cube root of 8. And this I know, the cube root of 8 is 2. Okay, now we can rewrite this equation. We have 2 to the absolute value of x plus 1 equals 2. Well, to the 1, now I have same base. I may equate exponents. This gives me absolute value of x plus 1 equals 1. Now remember, there are two possible options here. Either x plus 1 is 1, or x plus 1 is negative 1. So in the first case, if x plus 1 is 1, we can solve that x equals 0. And in the second case, we can solve x equals minus 1, which is negative 2. And so we have two solutions here, 0 and negative 2. The last page, I just want to talk about the number e. This will come up for us. It's probably the most important base of an exponential function in the calculus courses. It's approximately, so this is true, the number e is approximately 2.71828. But e is irrational. It's kind of like pi in the fact that it's irrational in that the decimal goes forever and it's not repeating. And so it's also true, for example, that e is approximately this. That's just carrying more decimal places. And I'm not sure how many I wrote down. It's what I could fit on the page, but this is many. Well, e can be defined in multiple beautiful ways. Maybe I'll just mention them. It's really a comment at this point. But for example, you can define e in, say, a Calculus 2 course. You can define e as a sum, say k equals 0 to infinity of 1 over k factorial. This is an infinite sum. And this you will see in Calculus 2. Another way, okay, this is also a Calculus 2 method for defining e. You can take e as a limit as n goes to infinity of 1 plus 1 over n to the n. Here you can take a limit of a sequence. So this is a limit of a sequence. This is another way to define E, but there's also many more. In calculus 1, I would define E in terms of a certain slope, but maybe I will just end this by saying, and many more. As I mentioned, it's the most important base in the calculus courses, and these two definitions of E, you do not have to worry about right now, but you will see them in calculus 2. So at this point, you can work on some of the exercises for lesson 2.2. Thank you so much.